Imagine a patient rushing into the emergency room in profound shock. Their blood pressure is plummeting, and they are suffering from violent rice water diarrhea. On paper, the presentation matches severe infectious cholera. But then you lean in, and there is a bizarre, incredibly distinct scent on their breath. It smells strongly of garlic. That scent shifts the diagnosis from a bacterial pathogen to an acute chemical infiltration. This is arsenic poisoning. In human toxicology, arsenic is classified as a pure xenobiotic. From an evolutionary perspective, human beings have no use for it whatsoever. Zero structural support to our bones, zero metabolic function to our organs, zero signaling value to our nerves. Because it lacks any physiological purpose, the ideal healthy human baseline is absolute zero. Since the body has no physiological pathway to utilize it, the poison must rely entirely on structural deception to bypass our architecture's most heavily guarded entry points. This structural deception occurs in two distinct ways. The first involves pentavalent arsenate. In this state, an arsenic atom is missing 5 electrons, and it arranges itself into a tetrahedral geometry that perfectly mimics inorganic phosphate. Our cells desperately need phosphate to build cellular energy, relying on specialized sodium phosphate cotransporter channels, or PIT1 channels, built directly into the cell walls. Because arsenate wears a perfect phosphate mask, the cell actively grabs the molecule and pulls it right through the front door. The second form is trivalent arsenate, an atom missing 3 electrons. At our body's normal pH, this specific chemical structure becomes completely electrically neutral. Because it lacks an electrical charge, it does not need to pick the lock on a specialized transport channel. It bypasses regulated ion pumps entirely, sliding passively through the cell's basic, unregulated water pipes, the aquaglyceroporin 7 and 9 channels. By utilizing structural mimicry for active transport and a neutral charge for passive diffusion, arsenic ensures complete intracellular infiltration without triggering standard biological alarms. Once inside, the cellular machinery tries to use that counterfeit phosphate. During glycolysis, an enzyme called GAPDHS reaches out to grab a phosphate molecule to build the next link in the ATP energy chain. Instead, it accidentally grabs the arsenate, creating an arsenate ester. A normal phosphate bond is tight and stores energy effectively. This arsenate bond is highly unstable. Almost instantly, surrounding intracellular water molecules attack it. It spontaneously hydrolyzes, shattering the connection immediately. When that unstable bond snaps, it releases heat, but it transfers zero usable energy to the cell. This spontaneous hydrolysis uncouples substrate-level phosphorylation. The cell burns its molecular fuel, yields zero ATP, and drives a localized increase in metabolic entropy. Meanwhile, the other form, trivalent arsenite, behaves in physical chemistry as a soft Lewis acid. This means it is an incredibly electron-hungry molecule that aggressively hunts for soft, electron-rich targets. In human architecture, that target is sulfur. Trivalent arsenite hunts down the vicinal sulfhydryl groups located on the dihydrolipoamide loops inside the pyruvate dehydrogenase complex. It binds directly to 2 adjacent sulfur atoms, forming a permanent, locked 5-membered coordinate ring. The pyruvate dehydrogenase complex is the primary respiratory gateway of the citric acid cycle. By simultaneously uncoupling glycolysis and physically gluing that gateway shut, arsenic drives an absolute cellular bioenergetics crisis, leading to a severe secondary accumulation of lactic acid. When the cell's energy grid fails, the liver attempts to neutralize the toxin using an intracellular enzyme called arsenic methyltransferase, or AS3MT. This enzyme relies on S-adenosyl methionine, or SAM, which serves as the body's finite methyl donor pool. The AS3MT enzyme strips methyl tags off the SAM molecules and attaches them to the inorganic arsenic, converting it into water-soluble metabolites. But SAM's baseline physiological role is maintaining your DNA. It places precise methyl tags on your genome to keep dangerous oncogenes permanently silenced. As the liver consumes all available methyl donors to process the heavy toxic load, the supply runs dry. This causes global genomic DNA hypomethylation. Without available methyl tags, the silencers fall off the genome and sleeping cancer genes wake up. To survive the immediate toxic shock, the liver sacrifices long-term epigenetic stability. This specific methylation trade-off cements arsenic's classification as a Group 1 human carcinogen. Today, the primary global vector for chronic endemic arsenic poisoning is deep alluvial groundwater. Millions of people bypass modern municipal filtration, relying on deep tube wells drilled into bedrock layers that naturally leach high levels of inorganic arsenic. When this contaminated groundwater is pumped to the surface for agriculture, it transfers the metalloid directly into the human food chain. The flooded, oxygen-poor conditions of agricultural rice paddies alter the local soil chemistry. This drastically increases the solubility of arsenite, turning the crop into a highly efficient environmental hyperaccumulator. Chronic exposure to this dietary source ravages the microvascular endothelial cells. It destroys the tiny blood vessels in the extremities, causing restricted blood flow and ischemic tissue necrosis, a condition known clinically as Blackfoot disease. Once the liver's clearance pathways saturate, the excess electron-hungry arsenite gets pushed out to the periphery. It binds permanently to structural keratin, turning the patient's skin, hair, and white bands on the fingernails, known as Mies lines, into a physical archive of systemic poisoning. To measure these trace clinical elements, laboratories use inductively coupled plasma mass spectrometry, or ICP-MS. The machine atomizes a sample in an argon gas plasma torch, burning at 8,000 Kelvin, stripping every molecule into pure ions to measure their exact atomic mass. The diagnostic process is extremely delicate. The rubber stoppers and glass in standard hospital vacutainers contain trace manufacturing arsenic that will immediately leach into the blood. Phlebotomists must use strictly validated metal-free royal blue top trace element tubes. Even with a perfect sample, a major analytical challenge remains. The machine's mass detector is blindly looking for anything with an exact mass-to-charge ratio of 75. But inside the extreme heat of the plasma torch, an argon atom with a mass of 40 will fuse with a chloride ion with a mass of 35. Because human blood is naturally rich in chloride, this argon-chloride polyatomic imposter forms constantly. It travels down the vacuum tube perfectly alongside true elemental arsenic, registering as an identical mass of 75 and triggering massive false positive toxicity alerts. To resolve this isobaric interference, engineers insert a kinetic energy discrimination, or KED, collision cell before the detector, flooding the chamber with helium gas. The fake argon chloride complexes are physically larger molecules. They collide repeatedly with the helium, bleeding off their kinetic energy until they drop out of the ion beam entirely, allowing the smaller, denser, true arsenic atoms to pass safely to the detector. Without the physics of kinetic energy discrimination, modern laboratories would be entirely blinded by the body's natural baseline chemistry. Yet even with an accurate mass spectrometer, clinicians face one final diagnostic pitfall: diagnosing a patient based entirely on a generic total urine arsenic lab value. Recent dietary consumption of ocean seafood or bivalves floods the human body with massive amounts of an organic compound called arsenobetane. Arsenobetane is entirely non-toxic. It is structurally stable and passes completely through human architecture without breaking down or hunting for cellular sulfur. This chart shows an HPLC speciation chromatogram. This process physically separates non-toxic organic seafood fractions from lethal inorganic pools based on structural charge, ensuring accuracy before the sample hits the mass spectrometer. Acting on a total arsenic number without performing HPLC speciation risks subjecting a healthy asymptomatic patient to aggressive chemical treatments simply for eating a lobster dinner. If the speciation assay confirms an acute inorganic toxicity, the treatment protocol requires immediate aggressive chelation therapy using deep intramuscular injections of dimercaprol or BAL. The thermodynamic mechanism of this chelation is highly specific. Dimercaprol is engineered with two adjacent vicinal sulfhydryl groups. These adjacent sulfur binding sites outcompete the cell's natural enzymes for the trivalent arsenite. This double sulfur design creates a vastly more thermodynamically stable bond, it prying the trivalent arsenite right off the pyruvate dehydrogenase complex, locking it into a water-soluble cage for renal excretion. The clinical architecture of this toxin rests on 5 core pillars: its pure xenobiotic status, its bioenergetic phosphate mimicry, the hepatic epigenetic trade-off, the mass spectrometer's isobaric interferences, and the necessity of HPLC speciation, arsenic reveals a profound vulnerability in biological design. The human body coordinates highly efficient metabolic and transport networks, but it cannot verify the true identity of every atom. By perfectly mimicking the geometry of essential nutrients, a simple inorganic shapeshifter can weaponize those exact networks against us.